Okay, for chapter 11.3, we'll have, this is the third way that we can decide if an infinite sum converges or diverges. So far, we have the geometric series test. That's the one where it has that very specific form, summation of a number to the n. And then you look at that number, call it R, and decide if it converges or diverges based on whether or not that number R is a fraction of 1 in the absolute value. We also have the theorem, which is also the limit test. If the limit of the sequence doesn't go to 0, then the sum doesn't converge. That only works one way. It doesn't go two ways. You can't test it to decide whether it's going to converge or not. And the example we had was summation 1 over n. That's the example we're going to work on here. But first, here's the theorem. If the function is continuous, f of x, and of course that's going to be the same function as we use for our terms in our sequence. And if it's a positive decreasing function, so it stays above the x-axis but it goes down on 1 to infinity, then letting that our terms in our sequence equal f of n, the infinite sum converges if and only if the improper integral from 1 to infinity of f of x dx is convergent. So here's where we have to work improper integrals as a way of proving it about something about an infinite sum. So let's see this theorem proved by looking at a couple of examples. Of course, that won't prove it for everything, but as we do the examples, I'll point out that it always works based on the continuous positive decreasing function hypothesis. So here's a sub n equals 1 over n. I remember that one. It's 1 plus a half plus a third plus a fourth. It looked like it was going to blow up to infinity. But here's how you see it. You draw the curve 1 over x. So that's the dotted line in that picture. That's 1 over x. And then looking at the x-axis, I've got the hash marks at 1, 2, 3, 4, 5. But they're all just with 1 rectangles. And so you can see the second rectangle hits the curve at 1/2. So the little arrows showing the shaded rectangles tell you the area of that rectangle. It's not drawn to scale. So for the first one, its width is 1 and its height is 1, so the area is 1. For the second one, the width is 1 and the height is 1/2, so the area is 1/2. Third one has area 1/3, fourth one has area 1/4. That'll keep going for area forever. So, and then here's the point. The sum, 1 plus a half plus a third plus a fourth, is bigger than the area under the curve. The reason is that those rectangles stick out. The corners of the rectangles are sticking out above the curve. So what it is that it turns out it's easier to figure out how big the area under the curve is than it is to figure out what's in all of those rectangles. And we take, for the area under the curve, we integrate from 1 to infinity, 1 over x dx. That's an improper integral, so we have to make it the limit as t goes to infinity, 1 to t. And then we get the natural log for the antiderivative. Plug in the t and take the limit, and we get infinity. Infinity minus 0, but that equals infinity. So the area under the curve is infinite. But if the area under the curve is infinite, the area that sticks out by the rectangles pointing out above the curve has to be infinite too. Anything bigger than infinity is also infinity. So we know therefore that the summation 1 over n diverges.